Good afternoon and welcome. My name's Tommy White, one of the developers of the MasterSeries, and today we're going to be looking at the Building Design Suite. The Building Design Suite consists of our core program, which is our frame analysis and model manager in Wind. That can receive information from third-party sources such as Revit, Tekla, even DXF files, StruCAD, and we can exchange those, and we can also send back out drawings to Revit in a round trip. And this is our core of the Building Design Suite. Onto that, we then add on our design components. So we have our steel design, our composite, including slim floor, our concrete, our timber design, our connections, and it's in the design component as an add-on, but it's really an analysis and design, our vibration and seismic, so you can look at your response factors in your floors if you so desire. We can also take that through and then produce RC details and connection details, and as I said earlier, we can also send it back into Revit and into StruCAD, into those different packages. The nice thing about Revit is full round trip integration. So single material environment for all types of structures: steel, concrete, timber, composite. Is extremely versatile and can do anything. It's not just for multi-story. It could do portal frames, it can do industrial frames, and we'll see that when we look at some of the different models. The nice thing about it being multi-material is you don't have to learn different systems for different materials. Not only is it multi-material, you can have all the different materials in the one structure. So as I said earlier, the core programs is our frame analysis with the model manager and the wind analysis. And then we can also add on to our core an optional finite element analysis if you want to do transfer slabs, meshes, shear walls, even look at your response of composite floors. The FE with the composite will actually work that out very, very accurately for you. And then you choose your optional design packages. So as I said, one model, all same interface, and they're technically advanced, and we designed to both Eurocode and the British standards. That actually means that you can switch between the two at the click of a switch to see what would happen if it was Eurocode or what would happen if it was BS. So if you're new to Eurocode, that's great because you can just quickly look back and say, yeah, it actually worked to BS as well, that's okay. So we then move on and look at our drafting, and as I mentioned, we have this superb bidirectional integration with Revit structure, and we also have links with Tekla, Multi-Steel and DXF and StruCAD. You can also generate quick GA drawings, and I will probably do a wee quick GA drawing for you, and RC details for the scheduling using the Master RC. So we're going to be looking at, as I said, all these different programs today. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different modules in this building design suite, and you don't need to take them all at once. That's important. So what does this all give you? It saves you time and learning because it's all one system. You don't need different suites for different packages, and because it's modular, you only take what you need. If you don't want to do composite design and concrete, just take it with the steel design add-on. If you suddenly get that job that you're required to do a bit of concrete in, you can add that module just via a phone call. So I'm using MasterSeries 2015-05. As you can see that we have a webinar on today. That's great, and I'm even there. So it's licensed to ourselves, and I'm going to come in and just quickly look at some types of frames that have been designed using our building design suite. So we have a steel and composite frame, a nice multi-story composite frame again. Yes, that is composite on the first floor and in these lower areas. I don't know what it is. It looks very good. If you know what it is, give us a shout there and we will tell everybody. This is a finer element model of flat slabs. Um, Again, finer elements for analyzing the shear cores in a building. And some more simple beams. And here we go, industrial frames. And this is industrial trusses. And don't worry, you wouldn't need to put all those trusses in one at a time. You can create one and then just copy it to save you time. And some more industrial work. Obviously some sort of conveyor belts running through this structure. It looks oh so horrendous. And I'm going to come into this model here and have a wee look around this, because this is a great model just for looking at what the model manager, the building design suite, is all about. So this is a typical or atypical frame. And the first thing we see is, yes, we do have a first floor fine element transfer slab because the columns at first floor are not meeting up with the columns at ground the first floor. If we turn on our 3D, we will see that we have shear cores, we have concrete ground beams, we have the yellow members are all our composite beams, and then we also have some timber. And we just rotate around and we see we have members sitting outside the structure as well as internally. So quite a nice, modern, sophisticated structure. So let's just turn that off, turn the 3D off, and I'm going to first of all look at editing, because clearly editing is one of the most important things. And yes, we can pull these in magically from Revit, magically from a DXF drawing. But what happens if you need to add something in, if you need to modify it? So let's go into the editor. Well, let's first of all go to a level 2. And we can see we got this big opening here and we've got some members, and I want to actually put in some additional members in here to create some sort of staircase. So I'm going to put a wee trimmer here and a trimmer along here, so I have a staircase walking up here. Or maybe actually I'll put it in here because it would be nicer looking coming up the staircase, coming up from here, coming up through to here. So geometry, define some new members, snap grid, and I'll just zoom right in. And I want to put a member coming in here at 1.8 meters back from this node. So I can just highlight and just type in 1.8. And before I continue, I'm actually not just drawing the line, I'm putting in the section size, and I'm going to say it's going to be 254 14631, and it's going to be pinned at its two ends. And now I can just snap directly onto that. Now I want to do another member, and this will just be the trimmer member is coming across here, and I'll just put the same section size in, and I'm going to have this coming in at midpoint, or I can have it coming in at third point if I so desire. I'm going to keep it at midpoint. We don't need to demonstrate drawing a member at an offset twice, and that's put that in. So we'll need to make some modifications to the structure later on to allow for that. Now, if I zoom back out again, we're not restricted to doing members off members in straight lines. If I wanted to continue this down and I wanted to continue that out, this member, all I need to do is highlight it, and I can come along and come out. Sorry, I need to take that one off. And now I can come along at whatever I need. So if I want an intersection between that member and this, I'd highlight that as well. And there I go. There's my node point to node point, and I can now draw a member. So I was just creating little instantaneous snap and tracking points the same way you would do so in AutoCAD. And in this case, it probably is, yes, it is exactly at the right position and straight onto that. So that's how easy it is to create new members. We can also create them in space if you want to, but why do you need to? You should be able to do any sort of member from another member. So we have lovely undo facilities. I'm just going to undo that, and undo that, and then undo the node generation. And that's me back. So that's how easy it is to generate. And as you can see, we have our full list of steel sections all built in. We can do timber and concrete sections as well. The composite will come on to later on. Now back out. We're only looking at this as our general overview of it. So now what we want to do is to look at the loading. And this is where normally in the past you would have come into member loads, and you would have said, right, let's take this member and we'll put on a load of 4.8 kilonewtons per meter run dead and 5.5 live and a 1.5 surfaces. We don't need to do that. That is very, very old school. Instead, what we do is we come along and we look at the whole building. So full frame, and we actually create what we call area loads. So let's look at the defaults. First things first, we have set up 1, 2, 3, 4, 5 levels, and we can give them different names. And notice the ground floor is at an origin below ground. It's re-zeroed that for me, and I have these, so I can call that level name, and I can call it Fred. So that's Fred's level, and then this is admin if you want to be looking at different levels. And for each level, what you're telling it is that for the transfer slab, it doesn't matter because it's FE, and possibly to make sure things sensible, we should say it's FE slab. So level Fred, it is composite, it's profiled, partitions 1 live, wet density, and our full loading. Superimposed dead, we're not going to have any, and it's 130 thick and a 5 live. The next level up, we only have 4 kilonewtons live. On the roof, we're down to 0.75, and on the roof, we will see that it is in fact not composite. And if you look at the loads, it's also got a 0 thickness, so it's taking some sort of crinkly tin, putting that into the dead loads. And in fact, we should really give it a dead load of 0.25 as well on that roof. So there we can define the basic setting up of each of the levels. And then we come along and we want to look at area loading panels, and this is where the magic starts to happen. We can take each roof or coming down, third floor, second floor and ground floor done together because they're same intensity. And remember, we messed around in here. So what I want to do is to go in and view level 2, and yes, I want to add in this as an additional, but there's an opening there for the walkway coming up from below. Maybe I should switch those around and actually say the walkway is coming up on the outside. That makes more sense with the staircase. And while I'm in here, I can do a lot of different things. It's very easy to create and to remove panels. And I can say, right, let's go in and let's just say make a local change. Take this panel, and I sometimes find it easier. You just draw the 3D so you can see the members easier. So taking this panel, we're going to change its direction, the span, that way. As we can see, we have all these different spans. But if I take that off and let's just look at the overall, clearly in this case you would actually want to span them all that direction. That makes a lot more sense for this composite floor. And we have a different intensity here. So if we wanted to make this panel have a different intensity, because it's a little plant room, I can again come along, highlight that one, and just say change its live load to 7.5. And I can then copy it to there and there. So that's all a plant room at my level 2. So very powerful and very flexible. Not only that, but we can define line loads, and we've already put edge loads onto all the members on the outside, except for these glazed corners, which are just going to have like glazing. And do I have any internal members? I probably have something else somewhere, but not on this level. So that's just a wee look at editing and applying and playing around with some loads. So back out the full frame. Now if I take off the 3D and look at my area loading that we have generated, we will see that we have different intensities at the different areas, and we can see the slab thickness, and we even put a floating slab, suspended slab on the ground coming off these ground beams. And I think they're actually spanning the wrong direction there. Those ones are spanning left to right because it's the same group as that one. And that means that I just need to go in quickly and edit. And it's not that one, not that one, it's this one. We don't want both sets defined at the same time. So let's just come in here, put this in, and just take all of those out. And then add in a new group called base. And as you can see, in defining them, we can define them one at a time, but that's not necessary. Just put it into front view, window the whole thing, look at it in 3D, and we can see that it's now spanning the direction we want to, left to right. And the loading is all coming from the main area. Again, we could stick some plant here if we wanted to, but no point repeating ourselves. So that's the area loading. The composite is very, very simple because the structure, when we look at a particular floor, has all these pins defined. So all the pins have been defined automatically as we worked through it. Very straightforward. We can define those pins ourselves by going into the member end release, and we could say, for example, take this one and take it off so it's now fixed or unfixed. If I was to take off all of these around here, I could just take one of these and then just copy the end release to those very, very quickly, and I can just window them as well to do them quicker and take them out and say proceed. There are also automatic facilities for creating end releases. So if I was to come down here and change them all from major only to major and minor and say proceed, they've all now changed to major and minor automatically for me. And it's identified where columns are. It's identified that that's got a column there, so therefore it's going to span from there to there and then from there to there. It's all hyper intelligent. So where do I go from here? We've looked at our loading, we've looked at floor loads, we've looked at varying the floor loads, we've looked at grid lines. Well, grid lines, they were all automatically generated, but I can come in at any stage and create my own. So if, for example, I needed to make this 9A, I would go to here and I would go 9A and then just tell it that it is from there to there. As you can see, it's not the same as there, which is 9B, and I could create a 9B if I so desire. So grid lines can be anywhere you want, and it's very, very useful. And likewise, the levels are set up automatically, and you can just click a node to create the level from that. But they're nice and neatly set up. And one of the advantages of using grid lines and levels is that when we generate our frame views, we have all of these generated for us. So we now have one on grid line 9A, which is quite interesting and doesn't show a lot because there wasn't a lot there, just that single member. But if we were to look at grid line 9, we'd see a lot more information going on, and we could at this point in time ask for a 3D structure. And you'll see the composite beams that we designated coming up in yellow, and the green ones being the structural steel members. The next thing I want to look at is really walking down through all this, and we want to look at our wind loading. So first of all, we'll look at our wind diagonals, and we'll accept 5 meters as the wind diagonal. If we're trying to be very, very, very economical in our design, we might decide to make that wind diagonal a lot larger, but it's not going to really make an effect on our two big shear cores that are resisting all the wind anyway. So we'll just leave that at 5. And the next item on that list is wind directions. So directions 0 to 270 with internal pressure and suction. And then after that, wind loading cases, which we will do later. And now we're going to go for our site data. And this is where I can have fun. I'm just unlocking the case. I'm going to come up here and say choose somewhere randomly. I could pick a town, say let's go all the way down to Chelmsford, or I can put in a national grid reference. Now luckily for me, I know of a great little website that allows me to put in grid references and postcodes and get the grid reference. So I'm going to go, and here we are, and it's one of my colleagues who uses the software over in Manchester. This is his offices, and if I hover over this again, I can now just come in and grab the grid reference, Control C, back to my program, and I just paste this in. And now I need to take out meters and tens of meters. I need to take out meters and tens of meters. So we're to the nearest 100 meters, and then just take out the 2 spaces, press enter, and there we are, back to where we should be. In Sale, I believe, is where we're at, south of Manchester. And since I've gone to the effort of creating that site, I'm going to lock that down for you. Now, in here, we are going to be working with the Eurocode. We can't use the standard and hybrid methods. We could go all the way down to the designer's guide with a wee bit of subdivision of the topography. But I'm going to stick to the basic, and the one most important thing is that we should always know our orientation of our building to north, so that we are able to use the wind loads accurately, and that's where I put my north, coming onto this at 40 degrees to the front. And that really is all I need to do in this point. Take this off. If I now look at my wind directions, I will see that I've got all this wind defined on the structure. Now I'm going to go to another structure in a minute and define that on this other structure just to save some time. But while we're here, what I do want to look at is just how good it is at determining the directions. And so for all the different directions, your W1, wind coming here, so we have positive pressure. We've got high suction here just after this drop, and you'll notice that these are different from the inside because they are a canopy, and it's understood that this is loaded from both sides and it's taking far heavier loads on each of those two sides. So what I'm going to do now is I'm going to go down and load in a slightly simpler frame so that I can continue on and do some analysis and some design. So if I go back to recent files, we'll take this little simple frame here. And this is a frame that we used to work with years ago, and I think it's come back into favor. And I go into Edit and a quick review of the loading, and we will see that we have just got some basic dead and live load on it in the two different levels. I have no dead because the dead comes from the slab, bear in mind, and we've no alternate intensities or anything, so we'll keep that simple. We don't need to repeat doing that again. But what I will do is we'll look at the wind loading instead. And I'm going to redo this all from scratch. So coming back, wind loading, panel generation, and this is where it gets fun. I'm going to kill all my panels. And normally you would come in and you'd say, right, let's auto pick a whole panel in apply mode. And you'll see that it can pick a whole panel, and I can come along and take this whole area and this whole area and this whole area, and that's quite good fun. Or if I kill all those and just use the panel rather than the auto panel, I can then do 1, 2, 3. So I can say they're horizontally spanning, insert another group 1, 2, 3, and say they are in fact vertically spanning, and then insert a third group and say 1, 2, 3, they are in fact two-way spanning. So we can create different directions of span on each member. Again, I'm going to kill that, and what I'm going to do is I'm going to ask it to generate the whole thing all by itself, and off it goes and generates that, and it's formed all the different panels, and it's found all the different surfaces, and it's generated it all by itself. And naturally, if you wanted to make this vertically spanning in this one, all you need to do is tell it that that one's vertically spanning. Go into search mode, find that one, and tell it that that is vertically spanning. Just turn off that, we don't need that, that's it. And this one, and we'll tell it again that it's vertically spanning glazing on these 4 corners or 3 corners. So there we go. All very simple, very quick, very easy to do. Now, loading cases. We've got our area loading, we've got our wind loading coming in, I hope. Have we? Let's just a quick check. W1, draw it. Yes, we have. We've got all these wind loading coming in, hitting the surface. Our CP values all calculated automatically, our Q intensity values. And even for those who are unsure, what are the assessments of A's, B's and D's of our wind panels, and take those all off. So loading cases is the next thing we really want to look at. And loading cases is something we've done a lot of work with recently, because with the advent of the Euro codes, it's getting awfully complicated. So number of cases. I have 53 cases. I'm going to come in and I'm going to delete a whole stack of cases. I'm going to delete from there all the way up to there and say delete those. Yes. Obviously it's a critical thing, so it's asking for confirmation. I've only got one loading case. And I could go in and add a case, give it a name, give it a combination and put the values in. But instead, I'm going to come back to the loading cases. I'm going to make sure that I'm working to the Euro code and I'm working to the British National Annex rather than the Euro norm, or you can create your own, copy them and apply them. So I'm in the Euro code. I'm happy. Auto generate cases. So it's going to come in and give me this brand new dialog. So these are my basic forms. Dead plus live will be giving me my dead plus my live one. Live load only is obviously live 1. Dead only for those who required. Dead plus live plus wind, and it's going to use these load factors, and dead plus wind. So what I'm going to do to save time, I'm not going to have my dead plus wind, just dead plus live plus wind, and I'm not going to have my dead only. You will notice for each of these that we are stipulating what we want. We want both ultimate and service, and we will be using equations 610 A and B, and we will find the equivalent horizontal notional force and its characteristic. So it's very, very detailed. And for live load only, it's service only we create. For dead plus live, again A and B. So I'm just going to come along and generate all these cases, and lo and behold, I now have 36 loading cases generated for you with the A's and the B's. And if we look at our loading combinations, we will see that we've got the 1.2s and the 1.35s in our combinations. So we have the A and the B loading cases. There's our 1.35s where we require them. So that's how easy it is to generate a frame. What I haven't even talked about is how the section sizes work. So just before we go and analyze it, look at our section sizes, and we will see that we have our UBs, our RSJs. You'll notice I actually, if you're a user of the system, I've removed some of the ones that I don't use. I've left the IP in just to show that we can do Euro sections, but I've taken the rest out because over here we don't use them that often, the circular, and I've gone for the parallel flange channels, but not the old-fashioned channels, because only if I was using historical work would I need those. And for any section, we can even take it and we can make it into a, let me see, 203, 203, make it 325 by 325, a encased section. So we have encased sections. We can do haunched and tapered sections, more for your portal frames, but no reason why you couldn't take an individual member up here and for the fun of it just put in 2 haunches. I know the section is roughly about 6 meters. I'm going to put in a haunch length of about 1.5 and 1.5 on the other end, and I now need to give it 2 serial depths. I'm going to give it 2 and 2. And here we go. If we rotate everything around, we will see that it is coming through, and it's just upside down because the member is coming the wrong way around, and I could go and change that and rotate that. It's only a graphical problem. It's not important from any other point of view. So if I move to this member, you'll see that's normal. This is haunched. If I went to properties, orientation, beta angle, I could take this member and I could rotate it. It's because it's going from left to right instead of right to left. 90? No, I don't think so. 180, and it now looks right to us in the design. So, sections, I've also in this frame given you a shear core and some concrete members and some simple steel at the top as we did before. So let's move through straight into design. But before we do design, we've got to analyze it. So analyze. Notice we're doing horizontal loads on the required loading cases. And we're doing our 36 loading cases. And very quickly, output. Fantastic. Very simple. Tabular. It's as simple and boring as you want it. It's all there. Every single member. And if you just window the whole lot, you can then pick the 2 or 3 members you're interested in and see those. So the more important and significant to us is the graphical. I always go to my graphical output, always, and check my deflections. And I'll check my deflections at a low-ish intensity. I'll put the structure in the plan view, or sorry, front elevation, and I will slowly rotate it and make sure I see no members bouncing down because they're unstable. They've got, a fixity problem. They're hinging where they shouldn't be and causing slight mechanisms. In this case, everything looks fine. Bending moments, all straightforward, all simple. Let's get down to one level, level 2, and we can see now that if we reduce our intensities, of course, we're getting our primary beams or secondary beams coming through, and we'll see as we increase the forces again. This end is a concrete frame, these first two bays, and therefore we're getting fixed end moments on our members. Everything else is pinned and stabilized by the shear core, the bracing, and this little concrete frame. Design. Into design, first of all, composite design. And I'm just going to stay with this level, and I'm going to look at the composite, because we can just say create all composite beefs, and it's created them all for us. And I can look at a simple composite member. So it's a secondary composite internal beam. What I need to do first of all is to think about it. I'm going to prop it during construction, and then coming through, I have these values all coming through from the frame analysis and not changeable. Likewise, all this. I have my studs and my mesh that I can modify, and the section size. So dropping right down, 127 is not going to do it. Walking up, and a 254 by 102.28 will do it. Is there anything nicer just above that? Well, it's not got the degree of shear connection we'd want, so it's costing us. So back down to the lighter section, and we're happy. It's more than 100 mil wide. We can get our deck and our studs welded 1 per trough with our default 192 mesh. And then we can look at our primary beams. We'll look at an internal primary beam, and we can see again we're getting failures, this time a lot bigger. I don't want to waste time. I'm going to sort by weight order, and I'm going to ask it to run up and try and find the first member that works. So it has found 457, 152, 52. And that works. If I was to say that the maximum height was 425, it would tell me that the deepest section isn't going to work. And even if I go up to a higher grade, that's not going to solve the problem. So the shear connection would be a problem, and we would need to change the spacing of the studs, possibly the other direction, to slacken off. There we go. At 120 centers for that shallower beam, we could make that section work. Now somewhere in here I believe I have some beams with openings in them, but for the life of me I can't find them today. But there's no problem, I can come along. There we go. There's a cell-form beam with openings, and it is very, very unhappy. Degree of shear connection is a problem, and if I look on down, it is really the shear connection is the problem. So again, shear connection, more studs, and you would need 3 per trough, which is possibly a wee bit unrealistic, so you would probably need to rationalize what section we want to use and what shear studs. Now I can go through and design all these, but I'm not going to take the time to do that this morning. I'm going to put this into plan view, and I'm going to scan for failures. So I'm going to scan for failures. So you saw how I could design one member, but what we're going to do is we're going to design them all automatically. Now it's not going to solve that shear problem because it's one that you should be trying to design out. So it's just doing those last few beams, and there we go, and there's the first of the members that failed, these cell-formed beams, which we need to just try and get a little handle on the problem. It's the openings themselves that are a problem. These openings are quite excessive. So heavier beam or stiffened is probably required, but I'm not going to work through all that today. That's for a composite design webinar. What I am going to do is going to scan these, and this will tell me how many members actually physically failed. And now I can ask it to show me all the unity values, and I can see all the values on the members. I can print that out, or only the failing ones. And it shows you it's just these ones here that were the ones that failed, and I suspect they're all the cellular beams. Yes, they are. So my cellular beams need a bit of work, and possibly it would make more sense to go to a built-up section and make it so that you have the holes the size you want, and you can then strengthen it as you want. So that's our composite design, and I'm going to say no to that. I'm not going to save it into design, this time into steel design. One interface, one frame analysis, one model. Now for steel design we need to go up a level because that floor is not got any steel, and if I come down a level, up a level, there we go, that's some steel here that needs designed, and we can see that these members are working quite well. The reason that it's highlighting all of them at the same time is because they've all been bound together. They all have been told to use the same data. So if I solve this one, let's look at this one. This has got deflection and local capacity failure, lateral restraints. It's going to be restrained by the deck. So I'm going to say fully restrained. So we need just to make it a bigger beam. So back to the auto design, and we will size it by size, and auto size current member, and the 406 by 31 now works. They have all the same definition of brief, but they are using different section sizes in this instance. So what I could do for this view is again go to my automatic, and again ask it to size all those members, and it's just running through them. And in this case it should be a lot easier because they're not composite. What are two of the other features I want to show you is the fact that, say for a column, when I size that column, so up here I could turn around and get away with a lot smaller, and it's been told that it must be at least a 200, so I'm going to tell it can go all the way down to a 100. So come all the way down. So coming up, that's the first one that works, a 139. If I now move down, you'll see that it's actually used that for the next two lifts because it's tied those three members together. They have been told to be the same size, and in fact all four of these, I believe, runs have been told to be the same size. So if I go and auto size that member, it's actually running through all the different groups, and with a limit of 100 now rather than 200, it's saying that this would work. So we're able to do a rationalized design. If I go up to one of these, sorry, the bracing members, again, they are coming in highlighting all of them at the same time, so that they are going to be designed at the same time to be the same size. So again, running through those, and we should see that it's the size those all to be the same 80 by 80s. What about these? They're also the 80 by 80 by 6. So they are okay. And since they've been told to be the same section size, if you now want to step in and say, well actually, I'd prefer a 100 by 100 by 8 just because it looks better. then that will also be used on all of them, including these ones. No, they're two separate groups. Interesting. We have decided to do those in two different groups, and I would elect to make those the same. So we can rationalize our design very, very simply. So that's some steel design. And again, just like in the composite, I could take a floor, roof plan, on plan please, and I could scan for failures, and then I get asked to print out. And it's giving you all the unity values of all the members, and this one hasn't been designed properly and needs to be updated because we didn't do a full design yet. And if I size that member, we can get that one now working, and if I do a scan for failure, it would now give me a revised set of values that shows that that one now works. And coming back, it just needs to update that data text. There it is. And again, another nice utility is it only gives you the worst in each section size or only the failing one, and we now know that that's the one that fails and that's the one we need to design. And we can then correct that one. That's got a fixity on that one rather than hunched. And remember this member over here? It's hunched. These are uniform. This one's hunched and this one's fine. So we just need to work on our deflections in those cases. But we're just having a wee look through the frames. Now, closing down, we've done steel, we've done composite. Just another quick analysis because we changed some section sizes very, very quickly. Design. Concrete design. Very simply, full frame. First member, let us do a auto size, and it's given us some reinforcement and some torsion, and it's all to the Euro code, and it looks horrible. Let's take one of the deeper big members. So what I'm going to do is do all visible members. I'm just going to run through all of these and size them all up. So it's going to have R bars top and bottom because it hasn't actually had anything sensible set in it yet. So I am going to turn around and tell it that we're going to use, yeah, that's very smart, mild steel main bars, and we're going to have high yield steel to Euro code and 8666. And if I now redesign that, that looks much more sensible. So we're not that heavily loaded. The spans aren't that great. So we're actually getting away with two 12s and two 16s. Two 25s in the top is all we need in our wee 350 wide sections. We could even at this stage come along and decide that we want to try and optimize this, so we could turn around and drop the section size down, say to 500, and narrow that down to 300 and see what that does to the auto sizing. And it's giving us still only two 25s, so we can see that it works very, very well. We are needing an extra bar on the bottom. I'm going to take that out and I'm going to make those into two 20s, and we can see again our capacity. Now again, in the Euro code it's slightly different to the BS in the way it designs, and that is covered in our concrete design module, our concrete design webinar. Some columns, very simple, and put some corner steel in, put some links in, and what's unhappy about? Probably the spacing of the bars, because this is very, very lightly loaded. Biaxial moment, we need a few more bigger bars. and seems strange, but let me see. There we go. Let the program figure itself out. So obviously from the 400 wide, the fact that there are some tension in the faces, it needs reinforcement at these distances. That would be far too far away, and that's a more economical solution. But it's just a demonstration of the flexibility of the program and our pad foundations. Now, we can take this and we can export our results, and obviously I don't have a lot of reinforcement at the minute. I'm going to just take them all. Some of them haven't been designed yet, so don't worry, they'll look a wee bit strange, but they will work. Just take all of my beams and I'm going to export that as a DXF file straight into AutoCAD. There'll be some blank members because we didn't actually go through and design them all. You remember that little problem we had, and here's the one that we've actually designed. There we go. That's it, fully detailed up for you. In this case with some torsional steel, because there is torsion in the beams because we haven't released any torsion, and our details of all our beam and our reinforcement all done, and the scheduling reusing bar marks as it can, and all nice and neat for you. So that's some AutoCAD drawing. I said I would also look at AutoCAD drawing of our GAs. I'm going to say yes, and I'm going to go to drafting. Now quickly analyze, because I want to analyze this. So what I want to do is I want to do a 2D export as a GA drawing, and I want to export, yeah, it's quite clever, plan at level 1, I'll take that, and I'll take my roof plan, and I'll take nothing else. And when I move over, I'm going to choose to have them on an A0 drawing at 1 to 100. Sounds reasonable. Now, my plan is going to be using a style called plan with forces. So it's going to be full outline, and we're going to have the shear load on the beams, and they're not at service, they're ultimate. And then the roof plan, we will do the same. We will have shear force on beams, and we don't need studs, and we don't want members in section, and we'll leave the members on. For this one, again, we'll just take the studs off just to keep everything nice and clean. And was this outline or that was full view? I'll just do that as an outline, a stick outline. So I'm going to take these two, send it out to AutoCAD, and in it comes into AutoCAD. There we go. And unfortunately I forgot to tell it to do them in plan, so I have got them as an isometric view. So we can see our members with our shear loads and our section sizes all drawn up, but we got them in an isometric orientation, which is not quite good. And this one came in as being with outline members. So I'm just going to close that, not save it, and I'm going to put that into plan. So we take the two views again very quickly. Now this one is an outline. We don't want outline, we want stick line. So a single nice broad thick line for each member. And we're going to export these two views into AutoCAD. Replacing existing, absolutely. And if you're wondering how my AutoCAD loads so fast, it's not the processor in this computer, it's the fact that I have an SSD drive, which makes things like that just so fast. So there we go. There's our nice little outline. Remember, stopping short. Now, 94s, 57s, sounds a bit vague. I'm going to cheat. one more time and do this a third time, and this third time I'm going to come in to my forces and say that I want them to the nearest 25, 25 and 25. So anything below those values of 25 won't be printed, and they will be printed to the nearest 25. So actually probably moment you'd want to the nearest 5 kilonewtons, or anything above 5 kilonewtons. So filtering out anything that's too small. And just to make sure that works, I knew I had some at 50 and some at 70, so make this at 50 as the filter. Well, that's the moment one. Sorry, not reading properly. Moment shear axial. So export one last time. Yes, as I was saying, I have an SSD drive. That's a solid state drive, and AutoCAD's installed on it. My programs are installed on it, so they do open very, very fast. In the mornings, it takes me less than 2 minutes to start up in the morning. And you'll see I'm not getting loads onto every single member because they're too small. But they're 75 kilonewtons, 100 kilonewtons, 125. So it is rounding them, and it's telling them that the shear loads are greater than 50. So anything else you would assume to be 50, and they were rounded up to the nearest 25. So it's giving you all the values you want, and in this case, little top section. So that's some of the simple stuff from the MasterCAD. Whoops, I always say that. Save drawing, no. We also have this interface with Revit. And what I did before I started was to come along, and if you go onto our YouTube channel, and we are just MasterSeries software, you'll be able to see the very good webinar Martin did there on Revit integration. And this is an old one. There is, I believe, a far more recent one. And if I just back out to, there we go, MasterSeries software, and if I take out the user bit, that will take you to, well, it knows who I am, so I'm seeing it as the developer rather than the user. And we can see these videos. Now, uploads, dynamic vibration is recent preview. So if I come along, these are the most recent uploads. There we go, Building Designer, BIM Revit 2014. Lovely little 17-minute video, not that long, taking a Revit model. And I will just mute this for you all, and you will see that as he comes along, he's able to then do an export through into MasterSeries, which he does very quickly. He opens it up, and there's that model come through with the cellular beams, and he's able to come along, do his design, change a few sections, in this case change their section sizes, so he's changing a couple of members, and then eventually he will come back into Revit with these updated members and through. So have a wee look at that video. So ladies and gentlemen, I would like to thank you all for coming along today. I would like to remind you that we are now using MasterSeries 2015, and if you aren't a user and want to try the software, please go onto the website and request to try a 30-day trial of any part of the software. Very simply, just asked for a 30-day trial. Let's try it now. Fill in your details and you will be sent to us. If you're overseas, your details will be sent to the most relevant person nearby. So if I go over to South Africa, it will be sent to our dear friends Alison Lawless, who represents us out in South Africa and surrounding countries. So fill that in, and she will then get a request to get you your 30-day trial and to discuss your requirements with you.